Hello, everyone. What I want to do now is discuss some applications of what we did in the last video, which is prove Fatou's lemma. So first of all, what I want to do is prove what most people consider and what most people call Fatou's lemma. So I'll call it the generalized Fatou's lemma. It was actually equivalent to what we did last time. And to be clear, most people call what I'm going to write Fatou's lemma. That's why I put in quotation marks. Particularly if you go to Wikipedia and look up Fatou's lemma, you're going to see this. So what is the statement? If we have a sequence of measurable functions, non-negative on E, thanks. Then the following is true. The integral of the lim inf is less than or equal to the lim inf of the integral. Now, this might seem much more general than what we did last time, because in particular, we're not making any claims of Fn converging to anything. But if you really think about it, this is really not any more general than what we proved last time. So in particular, we can cook up a convergent a convergent sequence of functions, kind of the obvious way. So let's set big Fn of x to be the infimum k of bigger or equal to n of fk of x. So clearly, this is increasing. Big F1 is the infimum of all these FKs. Big F2 is the infimum of k bigger or equal to 2. Of course, k is an integer here, et cetera, et cetera. So we keep taking the infimum of less and less and less functions. So this is definitely non-decreasing. It could be equal, but it's not going to be decreasing. Okay, and this is for all x and E. Thus, this limit exists. Everything is non-negative, so the infimums are non-negative, and thus this is non-negative. Could be infinity. That's fine. But in particular, this is measurable because remember the infimum of, well, we proved that the lim inf is measurable in the past. Just kind of reminder, infimums of measurable functions is measurable, and the limit of measurable functions is measurable, pointwisely. Okay, by the last video, i.e., Fatou's lemma. I'll write it like this. So it's a little messy, but this is the lim inf of Fn. So this is equal to big F. And so by what we had last time is less than or equal to the lim inf. Well, not of the little f's, but the big F's. Let me just make this a little neater. Better. That. There we go. Okay, and one thing to notice, kind of trivial, but it's really crucial here. This is less than or equal to Fn of x. Why? Well, n is in the set of all k bigger or equal to n, because n is bigger or equal to n. It's equal to n. So, this is a lower bound for all the fk of x's where k is bigger or equal to n. Well, fn is one of those. So this is less than or equal to fn. So this is true for any n whatsoever. So in particular, what do we have? Big fn of x is less than or equal to little fn of x. And so trivially then, or by the properties of Lebesgue integration, this is less than or equal to what we wanted. All right, and that proves it. And if you wanted to prove that, or if you want to show that this is equivalent to what we did last time, simply notice that if Fn converges to little f pointwise almost everywhere, then well, then the lim inf converges to f pointwise almost everywhere. And so you exactly get what we had last time. So yeah, we've basically proved that this is equivalent to what we had last time in the last video. Okay, not terribly deep, but something to be aware of. Okay, so next, I want to prove the very, very, very important monotone convergence theorem. Actually, before I do that, let me prove a very important consequence of what we just had a second ago. Actually, this is really a consequence of the Fatou's lemma from the last video, but okay, so if same thing, if each Fn is measurable, and Fn converges to f pointwise almost everywhere on E, and if each of these integrals are bounded by some positive m, so this is just some positive m, then that means that the integral of f is bounded by m. Okay. Okay. Well, if this is pointwise almost everywhere, then lim inf n goes to infinity. So this is true pointwise almost everywhere. And so that means so I guess I technically never stated that if two functions are equal almost everywhere, then their integrals are equal, but I'll leave that as a very easy exercise. Very, very, very useful to remember. And we basically implicitly have proved it in the past. It's very easy to prove. But yeah, so I mean, Fn converges to F pointwise almost everywhere on E, and therefore the lim equals F pointwise almost everywhere. So that means this is this lim less than or equal to this lim, and each one of these is less than M. So then, actually, it's sorry, not that it really matters much. So lim inf of M is just, well, M. So yeah, so this is really, even in research, mathematical research, this is very useful because this says to bound an integral like this, where we have pointwise convergence, all we need to do is bound each one of these. This is despite the fact that the integral of Fn in general will not necessarily converge to the integral of F. We've done in the past video oodles of examples where that's true. Okay, now let's get to monotone convergence theorem. All right. Yeah, and this is going to be surprising, but so what's the statement? And the proof is going to be surprisingly easy. All right, so suppose each Fn, same thing as before, is measurable. And for almost every x in E, we have the Fn's are increasing in kind of the sense we had right here. So we actually could have proved basically the generalized Fatou's lemma, what everyone else calls Fatou's lemma, from this monotone convergence theorem. But whatever. All right, so then if this is true, if this is increasing, then increasing non-negative sequences have limits. Could be infinity, but they have limits. Then this exists. This is not surprising. But what is surprising is we can interchange limits and integrals. So we had the whole slew of examples where you can't do this. Here we're saying as long as these are monotone increasing, then you can interchange limits and integrals. You cannot do this in general if it's monotone decreasing. For example, as we did before, let's say this is just 1 over n on R. So the limit of Fn is obviously 0. Okay. So this is 0. And so this is fine with no issue. So to be clear, these kind of examples don't violate Fatou's lemma. 0 is less than or equal to infinity. That's not very subtle. But yeah, in particular, the integral of f is not the limit of the integral. Sorry. Here, this is r, and this would be r here. Okay. Yeah, so in general, This is just false for a monotone decreasing sequence of functions. Okay. But it is true for monotone increasing sequence of functions. Right. Okay, so the proof is very easy. Just need a little refresher on limits and lim sups. Actually, I give it as a homework. It's enough to show that lim sup. This is very easy using the squeeze theorem in general. Whenever I have a sequence of non-negative numbers, I wanted to prove that it converges to a non-negative number. Things could be infinity here. It's fine. One way to do that is to prove this. Prove that that number I want to be the limit is sandwiched between the lim sup and the lim inf. All right. All right, so right. All right, so just being kind of maybe a little annoying with sets of measures. It's 0, but that's fine. This thing's being annoying. Okay. So let me just, well, okay, before I do anything, yeah. Okay, so this is true almost everywhere. All right. So that means I can pick a subset E prime of E where this is 0 and f1 of x is less than or equal to f2 of x, et cetera, et cetera. For all x in E prime. Okay, so that means this limit here, point-wise, exists. Again, it could be infinity. That is absolutely A-okay. In particular, this exists for all x in E prime. Okay. So what does that mean? That means Fn converges to F almost everywhere on E. Point-wise, almost everywhere. Yeah, I mean, it's being redundant to say that, but all right. Because we explicitly have a set E prime where we have convergence on E prime and E take away E prime has measures. Okay. Okay, we're done. We're basically immediately done. Or half of this is done. And the other half is actually even a little easier, believe it or not. Okay, so on E prime, this is increasing. So if it's increasing to F, then each Fn is less than or equal to F. Right. So, yeah, I'm basically done. So lim sup, then, E take away E prime has measure 0, so I can replace this with integrating over E prime. But on E prime, this is less than or equal to F. So this is what I need. So yeah, this is less than or equal to E prime of F. Again, each Fn is less than or equal to F on all of E prime. So lim sup of integral over E prime of F, there's no n involved. So yeah. And again, E take away E prime is measure 0. So we're done. Integral of F is less than or equal to the lim inf. Lim sup is less than or equal to the integral of F. So we've proved both of these. So very, very, very easy proof, but incredibly powerful. Okay, so as a consequence, we can prove some very nice properties about integration that otherwise would be a pain in the ass to prove. So in particular, let's prove that integration against a non-negative measurable function. Integration of non-negative measurable functions is additive. Let's prove that. So it's f g if these are both measurable. And of course, this by induction applies to the finite sum of functions, not just two of them. What's a little deeper, but still almost trivial by the monotone convergence theorem, is proving this for the infinite sum of measurable functions. So this is now pretty easy. Okay, so let's use the simple approximation theorem. So pick var phi n prime rather, not derivative, or I guess I could do tilde, doesn't matter what I call it really. Converging to F and G respectively. Now remember, we can pick these to be increasing to F and G. All right. Because these are both increasing, monotone convergence theorem says that this integral here is going to be this integral here. I'm using monotone convergence theorem here. So in particular, var phi n plus var phi n tilde is an increasing sequence of measurable functions, simple functions, converging to f plus g. But because it's increasing, monotone convergence theorem says I can interchange limits and integrals. So we know integration is additive when it comes down to the integration of simple functions. And yeah, sorry. Kind of the point. Both of these are simple. Right. Yeah. But just use monotone convergence theorem one more time. And that's it. Not a whole lot to this. Again, this var phi n converges to f, and it is increasing. So this is going to be same thing with var phi n tilde. It converges to g pointwise, and it's increasing. So, right. All right. So two more little results to prove. Very easy consequences of monotone convergence theorem. All right. The first theorem is as follows. And this basically says that, yeah, actually, let me leave this, prove something else. Okay, so let me extend what I just proved to, so again, by induction, this holds for any finite number of measurable non-negative functions. Let's prove it for a sequence of non-negative measurable functions, or rather the infinite sum of non-negative measurable functions. Okay, so if each fn then we have the following. And if you're in my AMAT 510A class, this was actually asked as a prelim problem, I think a year ago. And the idea is to use monotone convergence theorem. Okay, easy proof. Do kind of the obvious thing to form a non-negative increasing sequence. Let's just say big F. Let's say rather, yeah, whatever, I'll do that. Let's say this is just k equals 1 to n, fk of x. So this is trivially increasing on E. And the limit on E is going to be big F, which obviously is this infinite sum, which either exists as a real number or, sorry, a non-negative real number, or is infinity, because everything is non-negative here. So apply monotone convergence theorem again. This, write out like this. So we went from k to n, but that's whatever, doesn't matter. This is integral over f on E. Monotone, so I didn't do anything there. Here I'm using monotone convergence theorem. This is less than or equal to I'll just write it out. K equals 1 to n of fk. Well, as I said, I'm not going to repeat again. By induction, we proved, easy induction, that integration against a non-negative measurable function is additive as long as we have a finite sum of functions. And by definition, so this is just proved, except for that induction part. But that is a definition of this infinite sum. So very, very, very useful. I mean, incredibly useful. And to be clear, you know, like for the Riemann integral, this is fuzzy. This is, you know, really fuzzy stuff. But the Lebesgue integral is just so wonderful that as long as you have a non-negative sequence of functions, you can willy-nilly interchange infinite sums and integrals. I guess it's the novelty of this wears off pretty quickly when you do analysis research, but still, it still kind of amazes me how nice Lebesgue integration behaves. Okay, so two last results, and this is super useful in probability theory. So I'm going to prove that integration against a measurable non-negative function behaves like Lebesgue measure. That is extremely important in probability because, well, some of your favorite probability distributions are continuous random variables. The Gaussian distribution, you know, a whole bunch of Weibull distribution, a whole bunch of distributions that are continuous random variables. So probability of an event occurring is given by integration against that event of some probability distribution function. And you want that to behave like Lebesgue measure to be able to build up a useful theory of probability. Okay, so this is the following theorem. And go watch my last video to see how some of the stuff we have done can be applied to probability theory. I actually proved some non-trivial things there. I think I proved the probabilists' version of Borel-Cantelli, and I proved the Kolmogorov 0-1 law, which is not, I wouldn't say it's a deep result in probability theory, but it's a non-trivial result in probability theory. Yeah, so let's say E is measurable, and let's say its function is measurable. Okay. So I'll prove a whole bunch of things, and I'll state a whole bunch of things, prove one of them, and then you can prove the other two as an exercise. The proof is literally the exact same thing as a proof for Lebesgue measure, literally. So one, if En is pairwise disjoint sequence of measurable subsets E, then this is true. And probably the easy thing to do is, yeah, just do the monotone convergence theorem. I mean, yeah, it's just this easy consequence of the monotone convergence theorem. Like point blank, that's it. Two, so this is continuity of integration, which really uses one. And I believe uses that disjointification process we talked about, which is so useful. So if same thing, except instead of ENs are disjoint, let's assume they are ascending, but they're still measurable and subsets of E. So here I wrote it in square brackets. If it's not clear, this is square. Let me really emphasize that it is a square bracket. These are certainly not disjoint, they're ascending. I'll write it like this. So this is going to be the limit, just like it would be for Lebesgue measure. 3. And I'll prove 1 and leave 1 and leave 2 and 3 as exercises. So if these are measurable subsets of E, and this is descending, because I like to think we have kind of like a Russian doll thing going on, or nested rather. I forget what Royden uses. And just like with Lebesgue measure, you have to assume for Lebesgue measures, the measure of E1 is finite. So it's the same thing except for the intersection. Integrating over the intersection of the ends is this limit. Okay, again, I'm going to only prove 1, 2, and 3 are, well, they are good exercises, but perhaps more importantly, I do have to go to the bathroom, so I'll make this as quick as I can. Yeah. So remember that if A is a subset and it's measurable, then by definition, and this is quite useful, all right. Okay, so if I set Fn to be the following, just the characteristic function of this finite union of these disjoint sets, and because they're disjoint, this is going to be equal to the sum here. Yeah, so actually you don't really even need monotone convergence theorem. Let's just use let's be efficient and use what we proved before. So right. So this here, disjoint union, EKF. By definition, this is going to be the integral of this characteristic function over E. Okay. But because these are disjoint, you can check that this is going to be equal to this infinite sum. again, this crucially uses the fact that these are disjoint, pairwise disjoint sets. I mean, it's basically trivial check. Okay, but in particular, we have a sum of non-negative functions here that are measurable. So we can interchange sums and integrals. So this equals sum, k goes 1 to infinity, of e times this characteristic function. Again, I'm going to use what I just proved, or sorry, I'm going to use a definition. So this here, to be clear, is what I just proved here. It's this proposition. I just proved this. All right. Yeah, this is definition. And I'm going to use a definition one more time. And this is going to be the sum AKs EK F. Okay. Yeah, and if you're watching this, you have any questions on how to prove 2 and 3, just put a comment. But it really is virtually the same proof. It's not virtually, it is identical to the Lebesgue integral proofs. Okay, so in that regard, it is a good exercise to do. Okay, yeah, next up is integration of a general complex valued function. And for real applications to signal processing, physics engineering, Fourier series, Fourier transform, Z transform, we do want complex valued functions. So all right, so yeah, take care.